having to do something complex on a desktop-like environment, I know I can just call the contact API, for example, and have a very programmatic, simple way to grab that information. I can do that with billing. There's a whole host of things I can do. And in the capabilities themselves, for example, browser history, dialing, SMS history, there's a whole host of things that allows me to get information in a way that enables these attacks very easily. And more importantly than ever, there's a massive incentive for people to actually attack these devices. And we're very early on. I mean, the sky's not falling at the moment, but the platform is evolving so rapidly that the fact that I can directly monetize an attack through SMS or premium rate phone calls or indirect mechanisms such as selling your personal information. So if I grabbed your information and sold that to a spammer, in addition, grabbing sensitive information, we're actually finally seeing the tipping point of that motivation. I mean, hackers in the context of the bad guys, the criminal organizations are lazy, and they will do the simplest attack that nets the highest ROI. As we see the tipping point of it becoming easier on the mobile platform, then we'll see that change from the PC to the mobile device itself. So why won't mobile threats matter? We're skeptical people. We like skeptical people.
John, security people aren't skeptical.
So constantly we hear, okay, well, why should we even care about this? So mobile being fragmented is something we hear constantly. And I agree, mobile is fragmented. But when we look at today's world, how many devices are out there and how rapidly they're shipping. I mean, even a year ago, there was very, very few Android devices. It's absolutely exploding. There's nearly 150,000 to 200,000 Android devices shipping every single day. So when you think about, yes, Windows is this kind of singular platform that it's easier to attack, there's going to be 3 Windows or 4 Windows in terms of equivalent size and single OSs. So when we look at that, you have iPhone, you have BlackBerry, you have Android. There's going to be something that actually forgoes that fragmentation. In terms of sandboxing, yes, there's a sandbox, but sandbox doesn't always mean safe. And what we've seen OS vendors implement generally is great thinking, and we're super on board with the approach. We just want to make sure that people are tempered in their understanding of what's possible and what's not. And then in terms of attack surface, I mean, the attack surface, yes, in the context of mobile, could be looked at as small, but then you look at things like push services being implemented, messaging services. It's really becoming easier and easier to attack a whole host of things, ranging from the SMS protocol to things on the device itself to third-party services interacting. And we're seeing examples of this with third-party web-based services interacting with things on the mobile device that then serve as a vector. So we may find web-based exploits actually enabling compromise of the mobile device itself.
It's the question of why did we go do all this again? Ultimately, our goal is to keep people safe. I imagine that's why a lot of people do security research, is to help people better understand things. Especially in this kind of brave new world of mobile. We think it is different from the PC, and we think the approaches are probably going to be different from the PC. And I think for everyone involved in this, good data will lead to good decisions. And this is our small contribution to good data. What we want to be able to also do is identify threats in the wild. The vulnerability we talked about before, that's finding things like that, whether it be apps that are vulnerable or actual exploitation going on, that's really important to us. It's also kind of interesting to look at, because platforms take different security models, and to be clear, different security models does not necessarily mean more or less secure, they just mean different. And one of the opinions that I have is that threats will evolve with respect to the security model, and we can look into the data and see why we think that as well. And also, we want to see what apps are actually doing. And as we know, that this is not always the same thing that things say they're doing. And having data to actually help us identify things in the wild that have some sort of mismatches is good. And now we're going to go over quickly how we actually built this thing. Quick to orient everyone, there's 3 main pieces here that we want to talk about. One, we built a distributed crawler. It speaks Android Market and Apple App Store, so it talks directly to these marketplaces and gets metadata and downloads applications. We have a persistent data store, so we can actually analyze things as soon as we get them, or we can analyze them offline. For example, if we have a question we want to ask every mobile app that we've ever encountered. And we also built custom analysis tools because there's really not too much out there to analyze mobile devices, especially when we have talking a lot of OS-specific capabilities that play into the security model pretty heavily. So the crawler. We decided to build a distributed crawler. We first started as just kind of a single-threaded crawler, and we quickly found that analyzing every mobile app in the world can't do in one thread. So we have a job queue, and we have multiple jobs that can each queue other jobs. So first, we go enumerate applications. And this is actually a lot like you going to browse the App Store yourself. So you might go browse a category, and we'll see a whole list of applications. That's the enumeration step. Depending on the App Store, we may have another step to go actually pull metadata. So imagine you're browsing a category, you list all the applications, and you click on the applications, or a specific application, and you get a whole bunch of data about it. That's the second step. And the third step is, if it's a free application, we can actually have our crawler go and download it. And this thing, it's built in Ruby, and right now it's talking to 2 app stores, but don't be surprised to see it talking to more in the future.
And you can see how powerful this is. I mean, we first started just by doing manual research and looking at mobile applications. That's clearly not scalable. Kevin and I, there's not enough Red Bull to fuel that.
But we try.
But when we look at actually scaling that and being able to, in real time, look at every version of every application hitting in real time, not only being able to analyze threats as they come, but threats when we find new research to go look back historically at what happened and what was there, then this truly becomes a powerful tool.
So once we have the data, we're storing the application metadata, so we can actually go search it and do all sorts of fun stuff with it. We're storing that in MySQL. Application binaries we're putting on the file system. If you want to find the fastest way to make MySQL cry, throw a whole bunch of binary data into it. We didn't do that, but in projects past I had tried. Don't. And we're also tracking changes over time. So imagine we have an application, and you have 10 different versions of it. One potential threat vector is you have a great application, you wait till 1 million people download it, then you turn it evil. Right? So, download 100,000 applications. What's next? What are we going to do with all this stuff? So we built some tools. As John said, we quickly ran out of Red Bull, analyzing these all ourselves. We built some custom static analysis tools to actually look at the application binaries. So when we say we have a data set, we're specifically talking nearly 300,000 total applications, but nearly 100,000 application binaries that are active in the marketplace right now. And we're pulling interesting data out of them. The first is classes and methods reference. So these are API functions that the framework or the platform provides. We're looking at what sort of things are actually implemented in the code. On Android in particular, we're looking at permissions that the application has, and then also any sort of strings that are in the application. They're sometimes helpful to look at. We're going to look at Android first. So not only is Dalvik in Iceland, it's also in your phone if you have an Android phone. Dalvik is a virtual machine that's optimized for mobile. It's actually a really cool piece of technology, and you can spend hours reading about it. Not that I've done that, and it's effectively like a Java virtual machine with some kind of unimportant differences for our analysis here. The applications that you download on Android, for example, they are APKs. This is actually very similar to a jar format if you've ever seen a jar. And a jar is basically just a zip. And the main executable inside of an APK is called classes.dex. And this is an executable that runs in the Dalvik virtual machine. The other really important thing inside of an Android application is what's called the Android manifest.xml. It's a binary encoded XML document. It's a proprietary format, not exactly fun to parse, but there's Android framework code that can parse it for you if you need to do that. It describes the permissions that an application has and the application components. And there are some things that are really unique about the Android runtime that actually make this manifest fairly authoritative and important. And I think to understand how we did the analysis, let me go for kind of a brief dive in the Android security model. They did something very innovative, and that's forward declared permissions that are very granular for specific capabilities. So when you install an app, all of the permissions that app can or will be able to use are declared, and they're in front of you, and you get to say yes or no. This is different from a model where you either don't see what an app is doing or you're prompted to ask at a later time. And I think this is a great feature of the Android platform itself. Another really important point that I think these aren't the permissions you're looking for talk hit everyone, and I'm going to hit you guys over the head with it again. Android permissions and security is enforced at the process level, not the VM level. If you find a way to escape the VM and run something native, that's not an exploit, that's the point. That's how Android works. And it actually, it solves a lot of problems because, hey, we can run native libraries. We're not stuck writing Java and Dalvik. We can throw stuff to C if we need to. Hell, we can just throw stuff to shellcode, ARM shellcode if we need to. And that's all within the Android permission model. The other nice thing about this is the Android permission model is the Unix permission model. You're a process. If that process needs to access the internet, it just has permission to access the internet on the Unix level. It's actually quite nice. So with that in mind, how did we actually analyze applications? So the first step is looking at package permissions. It is a great kind of gating factor on what Android applications can do. We're going to assume that applications respect the permissions and that we're not talking about a root vulnerability here. If we have a root vulnerability, we have bigger problems on our hand than whether it respects the permission model. And we also do Dalvik static analysis to extract a whole bunch of stuff. And an example question we might ask an app is, does it have a specific permission and does it reference this specific API in its classes.dex file? And when we actually define questions, we define heuristics effectively. If we want to know if a device reads the device's phone, or an application reads the device's phone number, we say, okay, does it have the read phone state permission? And does it reference the telephony manager get line 1 number? Or we can run other arbitrary analysis on the fly. And I think we want to declare what the analysis we can do and where the future work is. And as we've said, apps shouldn't be able to exceed declared permissions. But if we know specific vulnerabilities, we can look for those as separate things. Also, capabilities can be implemented outside of Dalvik, so native code can interact directly with the IPC mechanism on Android, and apps can pull code directly from the internet. So we're obviously not going to be looking at code that's pulled directly from the internet when we're analyzing a binary statically. We're also not looking at evasive code. If a code is basically encrypting itself or modifying itself in some way, the analysis we're doing right now is not looking for that. Also, raw IPC calls. So if you're hitting binder directly, that's not in the heuristics we're looking at today. We're looking at the vast majority of apps who use the Android framework and are interacting with it. And of course, as we kind of move on into the future, there will be an near infinite amount of work to get more insight into bad things that are happening. So as we mentioned, we also looked at iPhone. The iPhone security model is fairly simple. There's process level sandboxing, and there's what I'll call App Store API enforcement. Namely that in order to get into the App Store, you have to do the right thing. You have to not use protected APIs, and you have to use APIs in a way that Apple deems good, which is not always a 100% silver bullet solution, but it works a lot of times. And also, interestingly enough, they do have ask for certain capabilities, namely location and push. So even though an application accesses the location API, it won't actually access your location unless the user confirms that you can. So like an APK, iPhone applications are really just zip files. The application binary is a Mach-O executable, which is the same executable format on OS X. And it's typically in the payload, and there's appname.app, which is the OS X and iPhone application package convention, and there'll be a Mach-O binary right inside of that. A quick detour into what Mach-O is, so you can kind of understand how we did the